Hello, I'm Hugh Manfield and welcome back to my science channel. Now, today is another installation of what Einstein got wrong. And today we're going to be talking about Bell's spaceship paradox. And this is a follow-up to my most recent video on fixing special relativity. Bell's spaceship paradox shows you what you get with Einstein's space denial philosophy. So, basically, Bell's spaceship paradox, we have two identical spaceships, and they're connected together by a thin, delicate thread. And we put an observer in the middle, and he sends the go signal, and both ships begin accelerating at the same time, and they accelerate up until relativity starts to take place and then become length contracted. And Bell's question was, what will happen? Will the thread survive, or due to length contraction, will the thread break? Now, the easy solution is to say, well, due to the startup kinematics, the thread will break. There's no way it could possibly survive the startup accelerations. But that's really a kinematics problem, and Bell is asking a relativity question. So let's assume the rockets can get moving, the thread survives the startup, and we end up with the rockets and the thread moving together and reaching higher and higher velocities. If we plot this on a space-time diagram, a spaceship at rest will form a vertical line. So they're starting out from rest at some distance between each other. We have space along the lower axis, time on the vertical axis. As time passes, they begin to move, and we show this as a slant. And as they get up close to the speed of light, the slant of the line will become parallel with the speed of light line. So this is how you would plot it on a space-time diagram. Now, one thing to note about this is that the way we're treating the space between the two spaceships is a Galilean transform. We're not using any relativity theory. This is all done with Newtonian kinematics. Stan would plot the location, starting point of each spaceship, and then he would compute based on their acceleration where he would predict them to be, and that would all be done with Newtonian kinematics. So the way this is plotted is a Galilean transformation, and that's something that's done without even thinking about it. So the next thing Bell said in the spaceship paradox is that as these ships become faster and faster and approach the speed of light, they will become length contracted. And if we plot the nose and the tail of each ship compared to the center, those lines will converge. And doing this is consistent with Einstein's space denial, apply only Lorentz transformations to material objects philosophy. And this is consistent with the way Einstein said we should do special relativity. We should apply the Lorentz transformation to the ships, but ignore the space in between. Now, one thing that's missing, and I'm not sure Bell considered this, is that the string itself is a material object. So that string is going to become length contracted as well. And I suppose we could plot the center of the string, and then the conclusion would be that the string ought to break due to the forces of relativity. But what if we put, instead of a string, or at least alongside the string, what if we put a very long spaceship? Now we're forced to contend with dealing with the space between the spaceships in a relativistic manner. If all the ships accelerate at the same rate, and the nose of the long ship tracks along with the nose of the front ship, and the tail of the long ship tracks along with the tail of the aft ship, then as they approach the speed of light, the entire space and the space between the ships must be length contracted if we consider them all to be moving in the same reference frame. And then that would say that the string does not break. So what's going on with Einstein's method of applying special relativity only to the material bodies is that in the case of the two small ships, we apply it to the ships but not to the space in between. And that means that now we're mixing the Lorentz transformation with a Galilean transformation. And you shouldn't do that in the same operation. If you're doing a relativity problem, it's going to be all Lorentz transformations. And if relativity isn't required, then you work it all in terms of Newtonian mechanics and Galilean transformations. But then, if we apply the Lorentz transformation to the entire reference frame, including both ships and the space in between, then how does Stan account for the apparent displacement of the ships as length contraction takes place? Let's consider the journey of a photon between two galaxies. And I've heard Roger Penrose talk about this. The experience of the photon is that it will arrive instantaneously at its destination. It's traveling at the speed of light, so time doesn't pass. So the experience of a photon is that the time of emission and the time of absorption are the same. It doesn't experience the transit. And the entire universe, or the entire length of the path that it transits, is compressed onto a single plane, and those 2 points are brought together due to relativity. But if we used Einstein's space denial philosophy to apply special relativity to the transit of the photon, we would apply it only to the individual stars in the galaxy and not to the space between the galaxy, and we'd end up with galaxies of flattened stars that are spaced in their original orientation, and we'd have these stretched out galaxies similar to what we're getting in Bell's spaceship paradox about the space between the two ships is apparently stretching out and the string will have to break. Applying special relativity, as Einstein suggested, to only material bodies leads to some rather bizarre conclusions. Using fluid space theory, we would say that once the two spaceships begin to move, they are in a different level of space-time. They do not share the same space-time as Stan the observer, who is at rest, and that his reference frame is no longer valid in saying what's going on with respect to the ships. If you want to know what's going on with the ships and the string, you have to get into their accelerated reference frame and follow them. And then the analysis would say that the two ships move along together, they become length contracted, or actually they don't even notice they're becoming length contracted, and the string remains intact. So what about the apparent displacements that Stan has to account for? Well, Minkowski tried to explain this, and in some of the accounts I've read, he described that what's going on, these apparent displacements, are part of the transformation. For example, you can see the full length of my pointer, but if I rotate it, now you can't see the full length, but you know that it's all still there. Now this is what's going on with the Lorentz transformation. Some of the length in the direction of motion is being converted into length along the time axis. And what that does is perform some sort of a rotation. So when I rotate the pointer and you can't see it, the apparent displacement of the two ends is part of the rotation. And that's what Minkowski's saying about a Lorentz transformation, that these apparent displacements come with the transformation and they don't need to be accounted for in any type of Galilean or Newtonian sense. So using Einstein's method of applying the transformations only to material bodies leads to some rather bizarre things, especially when you start talking about space trains. You get these concepts that the tail of the train has to travel faster than the nose for the length contraction to happen. Well, that's not true. Minkowski said those displacements come with the transformation. And in fact, the train is all still there, and if you were riding on the train, you wouldn't notice any length contraction, and you wouldn't notice that the tail had to be moving faster than the nose. And you could also, along the same way of thinking, conclude that if length contraction is actually shortening the cars, then the conductor would have to travel through the train as it accelerates and release the air pressure that's going to build up due to the length contraction. And that's just nonsense. The length contraction doesn't actually shrink the object, it just hides it from view from a different reference frame. The object is all still there, the train cars are all the same length, and you don't have to let out the extra buildup of air pressure. This is an example of why Einstein's space denial philosophy and applying special relativity only to material bodies is the wrong approach. The Lorentz transformations need to be applied not only to the bodies, but to the space in between. And that's how his theory of 1905 can be brought up to date. So until next time, I'm Hugh Manfield.